Hello, this is Mr. Stansbury. I'm going to take you through the 12F assignment. All right, so we start with number 1 here. A nest of ants initially consists of 500 ants. The population is increasing by 12% per week. How many ants will there be after 10 weeks? So let's try that one out. So we've got our A equals P times 1 plus R over N to the NT is a formula that should work throughout this whole section here. So we're looking for the end amount. That's the A. P is the original amount, which is 500. And then we 1 plus the rate as a decimal, so that's 0.12. Number of compound periods pretty much is always going to be 1 unless you start talking about money, and that's when it's like it'll be 12 if it's monthly, 4 if it's quarterly, so forth and so on. So anyway, this is going to be 1. And then this is going to be, it's increasing by 12% each week. So that means time is weeks. So if it's after 20 weeks, that's going to be 10. All right. Okay, so let's put that in. We can put it in just like it looks. 500 parentheses 1 plus, and it's really 0.12 divided by 1 is just going to be 0.12. All right, close our parentheses and then take this to the 1 times 10th power, which is to the 10th power, and that gives us 1552.92. So let's go with 1553. So 1,553 ants. I know that in the back of the book, they've got 1550 because they just rounded to the third significant digit. Okay, so this is a part I. Part I on A is going to be the same thing, but with 20 weeks. So it'll be A equals 501 plus 0.012. Again, if it's over 1, we don't need to necessarily write it. All to the 10th. So then we'll just bring this back up. And then really, let's see, I wonder if we can get this to, there we go. Turn this into 20. Push enter, and we get 4823.14. Okay, so we'll call it that. So 4,823 ants. Again, in the back of the book will give us 4820. Okay, but we're good here. It says use technology to find how many weeks it will take for the ant population to reach 2,000. So for that there, we want our A is now going to be 2,000, right? And that looks like 2066. Those are zeros. Close enough. And we want to know when it's going to equal 2,000. So we still start with our 500. We still have our 1 plus 0.12. And then now we're trying to figure out how long that's going to take. Okay, so what we're going to want to do is get this by itself as much as we can. So we divide both sides by 500. And we get 4 equals 1.12 to the t. Now really what this means is how long is it going to take for the population to be 4 times as big as it was originally. Okay, now we have this here. And whenever we have a power that is in the exponents, whenever we have a variable that's in the exponent spot, that's when we want to use logarithms, right? So take log of both sides, log 4 equals log 1.12 to the t, and this t now comes out front here. So really we got log 4 equals t log 1.12, and then now we just want to get t by itself, so we divide both sides by log 1.12, right? And we get that t equals whatever log 4 divided by log 1.12 is. So make sure you actually hit log of 4, because a lot of people want to say, oh, the logs cancel out. Yeah, remember, log's a function of some sort. So anyway, take log of 4 equals divide by log of 1.12, and we get 12.23 is the time. So it's 12.23 weeks is how long it should take for that to happen, for it to get to reach 2,000 ants. Okay? Or at least about something like that. All right, let's move on to the next one. That's number 2. The animal Eradicus is endangered. Since 1995, there's only been one colony remaining, and in 1995, the population of the colony was 555. Since then, the population has been steadily decreasing for 4.5% per year. Find the expected population in the year 2010. So we're still trying to figure out the end populations. That's A. The original population is 555. I'm going to multiply that by 1 plus the rate. Now, since it's decreasing at 4.5, really that rate is negative 0.045, right? Move that decimal over twice. So we end up getting negative 0.045, right? And then we're going to take that, divide it by the number of compounding periods, and that's just going to be 1. And then 1 times, and then this is the year 2010 from 1995. So 2010 minus 1995 is going to give us 15. Okay. So pull this up here. 555 times 1 really minus 0.045. Again, divided by 1 is just going to give us 0.045, all to the 15th power. So since we're subtracting here, this number here is going to be less than 1. So that's going to make this number actually start decreasing. So we should see a number that's less than 555 here, and we do, 278.19. So we'll go with, since it's population here, let's go to the nearest whole number. 278 of the animals should be left after 15 years. Okay. Part B, we get the year in which we do expect the population to have declined to 50. So that's the end amount would be 50. Still starts with 555. 1, I'm going to do this, minus 0.045. And then now we're looking for time. Okay, so first thing we want to do, get rid of the 555. Right? So we take our calculator and get 50 divided by 555. And that gives us 0.09009. So let's do this, 0.09 ... equals, and if we do 1 minus 0.045, that gives us 0.955 to the t power. Okay, and again, we want to get t by itself, so since it's up there, it's the exponent, we've got to take log. So we're going to do log 0.09 equals log 0.955 to the t. This t now can come out front. So we have log 0.09. Is it 0.09? Yeah. Equals t log 0.955. We got to get t by itself, so we got to divide by log 0.955, both sides. And away we go. Now, this here is the actual number. What you really want to make sure you do with this is do log of our answer. So you got to do log and then do second answer. And that will give you the log of 0.0900909, so forth and so on. Okay. And then we're going to take that and divide that answer by log of 0.955. And that gives us 52.27. Oops. Equals 52.27, and that is going to be the years, right? And that's from the original amount, which is 1995. So we got to take 1995 and add 52.27 years to it, right? And that gives us 2047. So it'll happen at some point in 2047. Okay? Okay, moving on to the next one here. That's number 3. Herd of 32 deer is to be left unchecked on a large island off the coast of Alaska. It's estimated the size of the herd will increase each year by about 18%. Estimate the size of the herd after 5 years and then 10 years. So we got A part I. So we want to know the end population. If we're starting with 32 times 1 plus 0.0, oops. If we take this 18, the decimal's right there, move the decimal over twice, so it's 0.18 divided by 1, which isn't going to change anything. And then this n here is also 1, right? And then we're just going to multiply it by t, the time, so this is 5 years. Okay, so let's plug that in. 32 parentheses 1 plus 0.12. Oh, sorry, 0.18. All right. And then we're going to take that to the 5th power. And we're going to have about 73 deer after 5 years. Okay. For A I, we're going to do the same thing but with 10 years. So A is going to equal 32 times 1 plus 0.18 now to the 10th power. Okay, so with this calculator here, let's see, I think I can go back, highlight that, push enter, and then now I should be able to edit that. So push a 10 in there, and then we push enter, and now it's going to be 167.5, so we'll just go with 167 deer. Is that what it is? Yeah, deer. Okay. And now, how long will it take the herd to reach size of 5,000? So that's part B. So now we know the end amount is 5,000. We want to know if it starts at 32 and it's increasing by 0.18. How long, T, is that going to take? Okay, so first thing we're going to do is divide by 32. Right, and away we go. So we take 5,000, divide by 32, and it's going to be 156.25 times the original size. That's what that 156 stands for. And that equals 1.18 to the t. So we got to log both sides, right? Because our exponent is the variable. So log 156.25. We want to know when's that going to equal log 1.18 to the t. T now comes out front, so we are at log 156.25 equals t log 1.18. Divide both sides by log 1.18. And that should tell us how long it will take. Alright, so we've already got the 156 in there, so I'm just going to do log. Oops, I did natural log. I want to do regular log of our answer. Gives us 2.19, and we're going to divide that by the log of 1.18. And that gives us 30.52. That's a 0. My zeros are looking like 6s, sorry. So 30 and a half years it'll take for it to increase up to 5,000. Okay? Alright, last one here. We've got a population of rodents was initially 400 but increased by 54% per month. Find the expected population size after 18 months. So we're looking for the end amount. We started with 400 and it's adding 0.54 per month. Again, the compounding periods, it's just every month, so that's just one here and one there. And we want to know what's the population size. Since this is increasing by 54% per month, we just want to know how many months there are, so it's going to be 18. You don't have to convert those months into years. Okay? So let's see, we've got 400 times 1 plus 0.54 all to the 18th power. That's going to be pretty big. 949,364. That's a lot. Okay, so yeah, that's a lot of rats. Okay, part B, find the number of months required for the population to reach 1 million. It's not going to take much past these 18 months, is it? Should be pretty close to that, it looks like. So let's take a look here. We've got we know that we're looking for 1 million, and it starts at 400, and it's increasing 0.54 on all to the t. So we're going to divide both sides by 400 if we want to find our exact answer here. So we get 1 million divided by 400, and we get 2,500. And when's that going to equal 1.54 to the t? Log both sides because our variable's in the exponent. Log 2,500 equals log 1.54 to the t. T comes out front. We get log 2,500 equals t log 1.54. Divide by log of 1.54 both sides. Right, and we get t equals, let's see what we get. So we're going to do the log of our answer, divide by log of 1.54, and look, there we are, 18.12. And that's going to be months, right? So that sounds pretty good because it took 18 months to get to 950,000 almost. So should take just a little bit longer than that to get up to the million. Okay? That's all there is for this section here. If you have any questions, please feel free to ask in class. Thanks.